Hello everybody and welcome to lecture number 9. So now we are pretty much done with differentiation. We've learned all the basic rules, we have learned the applications of those rules, we have learned how to do the opposite, anti-differentiation. Now we're on to the next half of calculus, which starts with the area problem, which was alluded to in the first lecture when I went over the two main problems of calculus, or in calculus. So the area problem can be summarized as follows. You have a plane region in 2 dimensions. So here we have the region underneath the curve y equals f of x from x equals a to x equals b, and the area that we care about is between the curve and the x-axis. So the problem is, how do you find the area of this shape? The issue is that this region does not have a formula, right? If it was like a hexagon or a trapezoid or a triangle or an ellipse or something like that, there are formulas and you can just plug in the appropriate values and get the answer. But there's no formula for this shape. So essentially we have a hard shape that has no formula to work with it. And our solution will be to approximate the area. So if I draw that same 2-dimensional region, right, is the exact same, as you can see. We want this area. Well, there's no formula for that shape, so what we use is an easier shape to approximate it. We have a formula for rectangles. So we break our region into some finite number of rectangles, and we use those rectangles to approximate the area. It won't give us the exact area, but it'll give us an approximation. The idea is mainly we have a hard shape that has no formula, so we approximate it with easy shapes that have formulas. And you don't have to use rectangles. You could use trapezoids or some other shape. As long as it's an approximation, it's doing the same thing. It's approximating the area. Use easy shapes with easy formulas to approximate the hard shape with no formula. And so the area under this curve is approximately the sum of all these rectangles. Now this is only an approximation. We want the area, namely the exact area. We don't want an approximation, we want the exact area. And so what you have is, if you increase the number of rectangles, then all those gaps, like right now, all the stuff that I'm filling in is either left out or it's over the shape. Right, all those shaded in areas are our error. We don't want any error, and so if we have more and more rectangles, they'll be skinnier, they'll fill in all those gaps, and what you want, ideally, is infinite rectangles. If you have an infinite number of rectangles, then there will be nothing left out or extra. Each rectangle will just fill up the space exactly. It's like if you colored in by drawing a bunch of individual lines. Nothing's left out, everything is filled in perfectly. But we can't have that, right? You can't have infinite rectangles, but what you can do is take the limit as their number approaches infinity. So we can take the limit of the sum of the rectangle's areas as their number approaches infinity. That's pretty much the outline for what we're going to do today. So just to summarize that, because it is an important concept in calculus, we want the exact area of this 2-dimensional plane region, but there's no formula for the shape. So we use easier shapes, shapes that have formulas, like rectangles, to approximate the area. But with any finite number of rectangles, there's going to be either overlap or underlap, I suppose. It's either going to be over the true value or under the true value. What we want is infinite rectangles. So what we do is we take the limit of the sum of all those areas of the rectangles as the number of rectangles approaches infinity. As you add more and more rectangles, you get closer and closer to the true answer. As the number approaches infinity, you get the exact answer. In order to turn this into a usable equation, we need to have a nice, concise way to express a sum of a lot of terms, right? Because our goal is to have the sum of an infinite number of rectangles, which means we need a nice way to express sums. So before we see where this leads us, let's take a quick sidestep into something called sigma notation. Sigma notation is a nice, concise way to express a sum of some number of terms. And I'll write out what it looks like. My pen needs to be replaced. There we go. So this left side of the equation is in sigma notation. This symbol right here, that's the Greek letter capital S, that's sigma. If you've taken stats, you know that lowercase sigma stands for standard deviation, uppercase sigma stands for sum. All those S words stand together. This right here, this is the index of summation. This is important. It's not always I. Sometimes it's J or K, sometimes it's N or M, but this tells you what the variable in your expression is. So whatever is right there, that is your index, that is what changes in your expression. This is your lower bound. It's the first number that you plug into your expression. The number on top is the upper bound. And what you do is you have this right here, which is the formula that gives the ith term of the sequence of the sum that you're trying to add up. So this is the ith term of the sequence that you are adding up. We'll do an example, which will make it all pretty clear. But this notation is a concise way to express the sum of A1 plus A2 plus A3 plus ... all the way to A sub n. I is the variable. First you plug in 1, or your lower bound, and you keep doing it until you plug in n. For example, let's do a sum. Let's do the sum from like 3 to 9 of I squared minus 1. So this means this is the formula of the sequence whose sum we're trying to find. We start by plugging this in for I. We finish by plugging that in for I. So first you plug in 3, gives you 3 squared minus I, or 1. Plus, then you go up by 1 every time. So after you plug in 3, you plug in 4. Then you plug in 5. And you keep plugging in numbers 6, 7, 8 until you plug in 9. And you add up all those terms and it gives you some number. But the important part is how you start by plugging this in and you keep going up by 1 until you reach this number right there. For us in this class, it will be unusual for us to ever start from anything besides 1. Sometimes we'll start from 0, but those are pretty much our only two options. So now let's do some formulas for sigma notation. Because eventually we're going to use sigma notation to approximate the area of our two-dimensional regions, so we need to have some formulas to do those evaluations. First one. If you have the sum from 1 to n of c times a sub I, where c is some constant, you can factor out that constant c. So just like limits, just like derivatives, just like antiderivatives, you can factor constants out. And you know c is constant because there's no I in it. Only terms that have I are changing. So if there's no I in the term, it's a constant term, you can factor it out. The second formula, or property, I should say properties. I'll say formulas and properties. The second property is also a property that we have from limits, derivatives, and antiderivatives. If you have the sum or difference of two different sequences whose sum you are taking, you can express that as the sum of a sub I plus the sum of b sub I. Both these two properties, by the way, make sense just algebraically. Like basically this first property says that if you take this sum and write it in expanded form, it would be c times a1 plus c times a2 plus c times a3 all the way to c times a sub n. And you can just factor c out. Right, so this is the left side, this is the right side, and they are equivalent. Let me just focus this a little bit, sorry. There we go. I think it's the exact same, but that's okay. The second one, you can also kind of show algebraically. If you were to do the expanded form of the left side, it'd be a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus all the way up to an plus bn. And since these are real value terms, doesn't matter what order that you add it up in, you can do all the a terms first. a1 plus a2 plus a sub n plus, and then all the b terms. Right, that's the commutative property of addition. Doesn't matter what order you add it up in. So essentially you can add up all the a's and then add up all the b's. So both those just make sense in terms of algebra. The third property, which is now actually a formula, also makes sense. This property says the sum from 1 to n of I is to show what the sum is. For example, before I give the formula, if you have the sum from 1 to 100 of I, you just plug first 1 into the expression, so it's just 1, plus, then you add 2, then 3, and you keep going up until you get to 100. Right? This is the sum from 1 to 100 where you just add up the index. This sum ends up being n times n plus 1 over 2. Now this was, I'm not even sure who figured this out, but a mathematician by the name of Bernoulli, he figured out formulas for any powers of I. So he figured out formulas for the sum of I squared, I to the third, I to the 15th, I to the 23rd. Any power of I, he produced a method to find an expression for it. That was done like in the 1600s, in the late 1600s. But a more fun story has to do with the mathematician named Charles Gauss, who's considered one of the top 3 mathematicians of all time. It's pretty much like Archimedes, Newton, and him. Gauss was called the Prince of Mathematics. When he was a kid, like 8 or 9 years old, he was already the smartest person in the room, doesn't matter what room he was in, and his teacher, just trying to keep him busy, told him to add up all the numbers from 1 to 100. And according to the story, he did the answer almost instantly. I think it's like 5,050. And what he did was he realized that if you group these terms, the first with the last, 1 plus 100 is 101. The second with the second to last, 2 plus 99 is 101. The third with the third to last, 3 plus 98 is 101. You would have 50 pairs of 101s. So the sum is just 50 times 101, which is this formula. If n is 100, it's 50 times 101. So we figured out this expression in a common sense way. In the posted notes on Stellar, I proved this formula out. It's not too bad of a proof, it's kind of a fun one to follow. The next one is harder to prove. The next property, also figured out by Bernoulli. Actually, one last note before we go to property number 4 on Charles Gauss. Charles Gauss did a ton of stuff in his time, but one of his big things that first caught the attention of people was that he proved the fundamental theorem of algebra. Which you may remember from your high school courses. This says like an nth degree polynomial has n roots, essentially. Why that's big is that some huge names in math tried to prove it. Like Leibniz tried to prove this theorem, and he was unable to. Euler, who's also one of the greatest of all time, he tried to prove this theorem, he failed to. There's a huge list of mathematical giants who tried to prove this theorem. All of them failed, and then Gauss was the one that actually proved it. He did a bunch of other stuff too. Like if you've ever heard of modular arithmetic, which is a huge part of number theory, that was him. He invented that way of doing math. But anyways, away from Charles Gauss. The sum of I squared from 1 to n is n times n plus 1 times 2n plus 1 over 6. This is tougher to prove. There's a method of proof called proof by induction. And it's easy to prove this with that method, but doesn't really explain why it's true. And we'll do one more power of I. The sum from 1 to n of I cubed is n squared n plus 1 squared over 4. And as I said, Bernoulli figured out a way to find any power of I, but we'll just do those 3. And you don't have to have those memorized. There's no need to memorize those. You might memorize them just by doing them over and over again, but if we ever have a quiz or an exam question where you have to use these, they'll be provided to you. They'll be part of the test. It'll say like, do this sum, and then a little side note, here's the formulas. Oh, I actually forgot one of the more important ones. Nope, I got them all, never mind. So those are the big properties. Let's look at one example, and then we'll move on. So let's find the sum from, we'll say 1 to 100 of 2i minus 1 squared times I. That's a squared right there. So you want to find the sum from 1 to 100 of 2i minus 1 squared times I. So what you don't want to do is plug in 1 to this, then plug in 2, then plug in 3. It would take forever. So instead we want to use these formulas, which make things easier for us. But in order to use the formulas, we have to multiply out our expression. We have to have a sum or difference of powers of i's, because we can find the sums of powers of i's, and we know also how to find the sums of terms. So first you multiply all that out. So when you multiply it out, it gives you 4i cubed minus 4i squared plus I. So again, you get that by squaring that and then timesing everything by I. And then if you wanted to, you could break this up. I'll put this in like blue because it's kind of the optional step. You could use those first and second properties that we learned to write this as 4 times the sum of 1 to 100 I cubed minus 4 times the sum from 1 to 100 of I squared plus the sum from 1 to 100 of I. And then use all those properties. But in practice, you just kind of go right from here to the answer. The sum of 4i cubed is 4 times the sum of I cubed. N's 100 here, so it's 100 squared, 101 squared over 4, minus the sum of 4i squared is 4 times the sum of I squared. N is 100, so it's 100 times 101 times 201 over 6. Then plus the sum of I, that's just n plus 1 over 2. So it's 100 times 100 plus 1 over 2. And then you would find whatever that answer is. So when you use these formulas, you have to multiply out your expression, and then it's okay to go right from here to the sum.